For 50 years, scientists believed the moon's underground caves were just theory, deep, dark voids hinted at by bizarre surface pits and unexplained seismic echoes from Apollo. Yesterday, NASA shattered that uncertainty. Using only a sledgehammer and a handful of sensors, they've revealed the first irrefutable proof of gigantic cavities beneath the lunar surface, some stretching hundreds of meters, large enough to hide an entire city. This is the announcement no one is talking about, published just hours ago, and it could turn lunar colonization from fantasy to reality, while rewriting our entire strategy for survival on Mars. So, what exactly did NASA discover about these hidden worlds, and why does it change everything we thought we knew about the moon? Taurus-Littrow Valley, the landing site of Apollo 17, has long drawn attention for its peculiar scars and shadows. Early lunar orbiters snapped images of pit craters, sharp-edged holes that seemed to plunge into darkness, their coordinates logged with growing curiosity. Some of these pits measured over 100 meters across, their depths impossible to gauge from above. Scientists wondered if these were simple collapses or the mouths of something far larger beneath the surface. But it wasn't just the pits. In the years after Apollo 17, seismic sensors left behind continued to record tremors, tiny moonquakes echoing through the valley's fractured crust. Occasionally, the instruments picked up faint, delayed signals. These echoes didn't fit the models for solid bedrock. Instead, the seismic waves seemed to linger, bouncing back as if they'd struck empty space. Internal NASA memos from the late 1970s mentioned so-called delay time clusters, but with no physical cave model to compare, most researchers dismissed them as quirks of the regolith or interference from surface debris. As new generations of planetary scientists revisited the data, the pattern grew harder to ignore. The Apollo 17 array, positioned near the Lee-Lincoln Fault, captured a series of echoes with time lags too consistent for random noise. Some signals arrived fractions of a second later than expected, suggesting waves had traveled farther, possibly around or through a hidden void. Yet without direct access, these hints remained just that, intriguing but unconfirmed. Meanwhile, high-resolution orbital images from NASA's Lunar Reconnaissance Orbiter mapped the region in unprecedented detail. Shadows inside pit craters stayed stubbornly black, even under different angles of sunlight, hinting at deep vertical drops. Thermal scans revealed patches that cooled more slowly than the surrounding regolith, another subtle clue that something was insulating the ground below. Taurus-Littrow, once chosen for its dramatic surface geology, now seemed to guard secrets that Apollo's tools could only glimpse. The evidence was piling up, but the question remained. How could anyone be sure what lay beneath the moon's battered crust? For decades, the search for hidden spaces beneath the lunar surface ran up against the hard limits of technology and budget. Early on, NASA's most promising tool was ground-penetrating radar, mounted on orbiters and, in theory, deployable on future landers. But radar waves, even at their most powerful, struggled to see deeper than 10 meters, barely scratching the surface compared to the scale of suspected lava tubes. Anything beyond that depth faded into static, leaving the largest voids invisible to remote sensing. Drilling, the other obvious solution, proved even less practical. The cost of landing and operating a drill rig on the moon soared into the hundreds of millions, and every kilogram of hardware squeezed out precious science payloads. Several ambitious proposals, one in 2009, another as recently as 2021, were quietly shelved when budget reviews revealed that a single borehole could eat up the entire mission's resources. Even the best-funded lunar missions had to settle for shallow cores, extracting mere meters of regolith while the real mysteries stayed locked away. Thermal mapping offered some hope, tracking how quickly the ground cooled or warmed after lunar night. But these measurements only hinted at insulation effects, not the shape or size of underlying cavities. Without a direct probe, every method left room for doubt. The Lunar Reconnaissance Orbiter's radar, for all its sophistication, could only confirm shallow layering and occasional anomalies, never the vast, city block-sized tunnels that some models predicted. As late as 2024, internal NASA reviews labeled the search for deep caves as high-risk, low-return, with recommendations to focus on surface exploration instead. The result was a scientific stalemate. Instruments could map the surface in exquisite detail, but the moon's true underworld remained out of reach, too deep for radar, too expensive for drilling, and too ambiguous for thermal scans. This impasse forced researchers to look for a new approach, one that could finally pierce the lunar crust and reveal what lay hidden below. Thomas Waters and Nicholas Schmerr stood out in a field of lunar science dominated by billion-dollar hardware. Their approach was almost primitive by comparison. Instead of launching advanced radar arrays or drilling deep into the moon's crust, they brought a sledgehammer. The idea was simple: strike a metal plate on the ground, let the shock waves ripple through the regolith, and listen. If there was empty space below, the waves would change, slowing down, bouncing back, or even vanishing for a split second. The test setup looked more like a construction site than a high-tech lab. A row of seismic sensors, small, rugged cylinders called geophones, was laid out in a straight line, each one spaced a few meters apart. The team reused core components from Apollo 17's seismic toolkit, updated with modern amplifiers and digital recorders. Each hammer blow delivered about 300 joules of energy, enough to send a clear pulse through the ground but safe for delicate electronics. The sensors recorded the tiniest vibrations down to millionths of a second, capturing not just the initial wave but every echo and aftershock. The workflow was methodical. Waters would swing the hammer, striking the steel plate with a sharp metallic ring. Schmerr and the engineering team monitored the data in real time, watching for telltale delays or distortions in the returning signal. Each test site required dozens of strikes, stacking the results to drown out background noise from surface pops and distant lander activity. The array would be shifted, the sensors repositioned, and the process repeated, building a three-dimensional map of the subsurface layer by layer. What made this method so powerful was its elegance. Traditional seismic surveys on Earth rely on explosives or heavy drop weights. But the moon's low gravity and lack of atmosphere meant that even a handheld hammer could probe surprisingly deep. The energy from each strike traveled farther, with less interference from wind or water. By analyzing how long the waves took to reach each sensor and how their frequencies shifted, the team could spot places where the ground was hollow, where a city-sized void would slow the signal or send it echoing back in a unique pattern. The breakthrough came during field trials in Arizona, where lunar-like basalt flows provided a test bed. After a sandstorm threatened to ruin the experiment, Schmerr improvised by swapping in consumer-grade accelerometers and solar chargers. The makeshift system outperformed NASA's standard equipment, recording subtle phase delays that matched the signature of an underground tunnel. The data stunned the team. If the same patterns appeared on the moon, it would mean that vast, hidden spaces could be mapped with only a hammer and a handful of sensors. No drilling, no billion-dollar payloads, just clever engineering and persistence. By September 2025, the method had been refined for lunar deployment. Automated hammers could be operated by robots or astronauts, and lightweight sensor arrays could be scattered across the surface by small landers. The energy required was minimal, the hardware robust, and the results immediate. For the first time, researchers had a tool that could reveal the moon's secret architecture, one hammer strike at a time. Inside the Taurus-Littrow Valley, seismic echoes traced a hidden world. The sledgehammer tests revealed voids stretching over 100 meters wide, longer than a football field, and extending for kilometers beneath the surface. These are not narrow cracks or shallow hollows, but vast chambers, their ceilings thick enough to shield against the deadliest threats in space. Cosmic radiation, a constant hazard on the moon's surface, drops to negligible levels inside these caverns. The rock overhead, sometimes tens of meters thick, blocks high-energy particles that would otherwise tear through unprotected habitats. NASA's radiation models show that a base built inside one of these chambers would receive less than 1% of the annual dose measured on the surface. For future lunar settlers, this means no need for heavy shielding or deep-buried bunkers. Nature has already done the work. Meteorite impacts, another constant danger, are also neutralized. On the surface, even small rocks traveling at tens of kilometers per second can punch through metal and regolith. Underground, the threat vanishes. The same basalt flows that once carved out these tubes now form a natural armor, tested by billions of years of impacts. Structural engineers studying the seismic data estimate that most of these voids could withstand even the largest meteorite strikes recorded in the region's history. Temperature swings on the moon are brutal. Daytime highs soar above 120 degrees Celsius, while lunar night plunges to minus 170. Yet within these caves, the environment is transformed. Thermal models based on diviner radiometer data predict a steady interior temperature near minus 20 degrees Celsius, regardless of the chaos above. While not warm by Earth standards, this stability is a game changer for life support. Heating a base from a constant sub-zero baseline is far simpler than battling 300-degree swings each lunar day. Habitat designers can focus on efficient insulation and targeted heating, rather than engineering for extremes. The sheer scale of these spaces is what stunned even veteran scientists. Nicholas Schmerr, quoted in a NASA press release, called it the first time we've mapped voids this size with such simple tools. Kilometers long, wide enough to house entire city blocks, all naturally protected. Thomas Waters, in his own words, described the moment as proof that we can find safe havens for future explorers with nothing more than a hammer and a good ear. For mission planners, the implications are immediate. Instead of hauling tons of shielding and habitat modules, Artemis crews could focus on surveying entrances, mapping internal networks, and testing airlock systems. Private companies are already drafting plans for robotic scouts to stake claims on the largest chambers, hoping to secure future sites for mining, science, or even tourism. The discovery has also caught the attention of international partners and rivals, with China and Russia reportedly retasking their own lunar missions to investigate these coordinates. The Moon, once imagined as a barren wasteland, now offers a new frontier, an underground world, ready to shelter the first permanent cities beyond Earth. The question is no longer whether these spaces exist, but how soon humans will move in. And as excitement builds, another possibility looms. Could the same method unlock similar havens on Mars, accelerating the next giant leap for settlement across the solar system? The Sledgehammer seismic method, proven on the Moon, is now being adapted for Mars. In 2024, engineers tested the system near Flagstaff, Arizona, using basalt flows and dusty soil to mimic Martian conditions. The results showed that even with higher regolith porosity and weaker gravity, a simple hammer strike could send seismic waves deep enough to detect buried voids. On Mars, the technique requires only minor adjustments, slightly heavier weights, automated actuators, and ruggedized sensors to withstand the planet's wild temperature swings. Martian lava tubes, first identified by orbiters as long, dark skylights in regions like Elysium Planitia, could stretch for tens of kilometers beneath the surface. These natural tunnels, carved by ancient volcanic activity, offer the same promise as lunar caves: thick rock roofs for shielding, constant temperatures, and access points already mapped by robotic scouts. The latest models predict that a 10-kilogram drop weight, deployed by a small rover, could probe to depths of 15 meters or more, enough to reveal cavities the size of subway stations. Sensor arrays, spaced at intervals along the Martian surface, would record the seismic echoes from each strike. The data, processed on board or relayed back to Earth, would show where the ground is solid and where it rings hollow. This approach bypasses the need for deep drilling or heavy machinery, making it ideal for early scouting missions. NASA's engineering teams have already integrated these systems into the design of upcoming landers, aiming to deploy the first seismic scouts to Elysium coordinates as soon as 2027. For planners, the implications are immediate. With a proven method for mapping underground shelters, the timeline for establishing a permanent base on Mars could accelerate by years. Instead of waiting for complex infrastructure, explorers could move directly into natural bunkers, protected from radiation and dust storms from day one. The path to the Red Planet's first underground city now looks far more direct and far closer than anyone predicted just a few years ago. In the wake of NASA's seismic breakthrough, the race to claim and develop lunar caves has shifted from science fiction to urgent reality. Artemis mission planners are already drafting schedules for robotic scouts, aiming to deploy the first cave prospecting landers by 2027. These missions will target mapped entrances in Taurus Littrow and Mare Tranquillitatis, sending automated hammers and sensor arrays to chart the most promising underground networks. The data will guide where future crews can safely establish outposts and which voids offer the best protection for long-term habitation. Policy experts warn that the legal landscape is far less settled than the engineering. The Outer Space Treaty, signed in 1967, bans national appropriation of the Moon, but says little about private or commercial claims to subsurface resources. No international agreement defines how or if a company can secure exclusive rights to a lunar cave. In the absence of clear rules, several U.S. startups and aerospace giants have already filed confidential proposals with NASA's Commercial Lunar Payload Services Office. Their goal? To lock in access to the largest chambers before international rivals arrive, staking early claims on what could become the most valuable real estate off Earth. Industry analysts now project that the lunar habitat market, including construction, logistics, and energy for underground bases, could top $2 billion by the early 2030s. Investors are watching closely as Artemis planners weigh cave sites for the first semi-permanent base, which NASA documents place in the mid-2030s. The stakes are enormous. Whoever controls access to these natural shelters will shape the future of lunar mining, science, and even tourism. The legal ambiguity only adds fuel to the competition, as companies and nations maneuver for first-mover advantage in a domain where property rights remain undefined. With robotic prospectors set to arrive within 2 years and base construction on the horizon, the moon's underground cities are no longer a distant vision. The decisions made in the next decade about who surveys, who builds, and who owns will define not just lunar settlement, but the entire economics of human expansion into deep space. On September 26, 2025, NASA confirmed the existence of underground cavities beneath the moon's surface, measuring over 100 meters wide and several kilometers long, using a seismic sledgehammer technique first tested with Apollo 17 equipment. For over 50 years, these lunar voids were only hinted at by pit craters and unexplained echo delays in the Taurus-Littrow region. Earlier methods, including radar and drilling proposals, failed to penetrate more than 10 meters, leaving the true scale hidden. Today, scientists like Thomas Waters and Nicholas Schmerr have delivered hard evidence of spaces large enough to shield future lunar outposts from radiation and micrometeorites. Yet, questions remain. The full extent, stability, and distribution of these caverns are still being mapped, and some Apollo-era seismic data remain classified. NASA's findings have already redirected Artemis mission planners and accelerated Mars habitat research, with the first robotic scouts targeting lunar cave sites by 2027. As these discoveries reshape timelines for Moon and Mars colonization, one fact is clear: the search for safe, sustainable habitats beyond Earth has entered a new era, grounded in evidence gathered beneath our closest neighbor's surface.